Organic chemistry, unit 4. Organic chemistry is actually the study of compounds of carbon. Organic chemistry actually is based totally on carbon. There are some carbon compounds in organic chemistry as well. When they talk about that, they are actually hinting towards carbon monoxide, carbon dioxide, the carbonate ions, and the hydrogen carbonate ions. These are components made up of carbon but are not included in organic chemistry. So we won't include these in here, okay? So moving on, there are more organic compounds than all the other compounds put together. So that means inorganic chemistry cannot get up to the count of organic chemistry, and you'll get to know on a couple of pages ahead why is that so. These compounds include naturally occurring ones in our bodies, proteins, DNA, fat, and the artificially made ones like plastics, dyes, drugs. But most of the time, the things that we are interacting with on daily basis, the clothes, the things we use all the time, the things that we usually purchase from the market, most of them are organic compounds. They're mostly derived from chemicals obtained from crude oil, as crude oil is used to not just refine and then can be converted into the oil we use for fuel purposes most of the time, but it's more than just fuel for cars and electricity. Organic chemists are actually involved in synthesis of huge varieties of new compounds. This includes drugs, this includes medicines, this include different other substances which can be used in daily life for many different purposes. Even the products that we use for our hygiene, for example, shampoos, lotions, and stuff, they are mostly organic compounds as well, not just the medicine we eat. Okay, so moving on. The first chapter in this list is Introduction to Organic Chemistry. So we are going to introduce you to organic chemistry. As you already understand, organic chemistry would be mostly carbon-based compounds. The ones that I have already listed are also written over here. Organic compounds can exist as chains like this. Branch chains means they might have branches on the chain, top and bottom, like this one and this one. Okay? And they might have rings. Organic compounds can also be arranged into rings like this. And then they have other parts on this ring too. So we call these rings. Okay. So organic chemistry, as soon as So I was saying, as soon as you start doing organic chemistry, you're suddenly faced with a whole lot of new compounds with strange names, unfamiliar ways of drawing, and it can be a little bit scary, but don't worry. Slowly, you'll get everything falling into place, all right? So the secret at the beginning is to spend a lot of time exploring the subject, understanding names, understanding structures, how to draw them, making models, and some basic definitions. So we are going to start with the basic definitions first. In organic chemistry, we will mostly be handling with hydrocarbons. Hydrocarbons are the simplest of organic compounds. As the name suggests, they are known as hydrocarbons because they would be made up of hydrogen and carbon only. Just two elements from the periodic table. And you will be amazed how we can rearrange these two elements in billions of different compounds. The word only is important here. Virtually all organic compounds contain carbon and hydrogen, but hydrocarbons contain only carbon and hydrogen, which means other organic compounds may contain oxygen on top of carbon and hydrogen, may contain nitrogen, may contain sulfur, may contain phosphorus, or even halogens. So these are the most common atoms along with carbon and hydrogen in organic compounds, all right? So the carbon atoms joined together may be joined with single bonds, like in this case, may be joined with double bonds, like in this case, may be joined with triple bond, like a case like this, all right? So there can be many different kinds of bond that they can be joined with. What we do is that organic chemistry can be described as saturated, which only consists of carbon-carbon single bonds, carbon-carbon single bonds, not carbon with other elements, and unsaturated, which may contain a carbon-carbon double. This is a mistake in the book. It should be carbon-carbon double or carbon-carbon triple bond, all right? These will be discussed in upcoming chapters, okay? So moving on, types of formulas of organic molecules. The first type of formula is empirical formula. This one is the simplest whole number ratio of atoms in a compound. We're done with this type. You already know that if a substance such as ethane has a formula of C2H6, we can simply convert it into CH3 as empirical formula. Now this one is the molecular formula, which is explained right at the bottom. And this one is the empirical formula, which is the simplest whole number ratio of atoms in a compound. Molecular formula, on the other hand, as this definition just counts the actual number of each type of atom present. So this formula tells me that carbon, there are 2 atoms of carbon and there are 6 atoms of hydrogen. While empirical formula gives me a simplest whole number ratio CH3, meaning there can be other forms of this molecular formula present. All right. So there's another example. Butane is actually 4 atoms of carbon and 10 atoms of hydrogen. However, the empirical formula can be converted into C2H5. Ethene is C2H4. The empirical formula can be converted into CH2. All right. So molecular formula is actually a multiple of the empirical formula itself. For example, if CH2 is multiplied by 2, it becomes C2H4. If C2H5 is multiplied by 2, it becomes C4H10, right? So the same thing can be seen over here. With molecular formula CH2, with empirical formula CH2, the molecular formula could be C2H4, C3H6, C4H8. So the multiples can be many different ones. That's why empirical formula is not considered as a complete formula. It's just a whole number ratio. These two compounds have same molecular formula but different structure. In this case, we have a separate word. And the term that we use, we're going to explain it much more detail ahead, but these structures are known as isomers. The phenomenon is known as isomerism, in which 2 compounds have the same molecular formula, but they have different structure. Like this one is also C4H10, and as you can see, the black balls represent carbon, the white ones represent hydrogen. They're in a straight row. And this one is somewhat different. They are arranged like this, right? And they are arranged like this. So we call them isomers. The phenomenon is known as isomerism. On upcoming pages, we're going to discuss this phenomenon in much more detail. But continuing for now, molecular formulae are used very rarely in organic chemistry because they don't give any useful information about the bonding in molecule. Instead, what we do is that most of the time we're going to come up with structural or displayed formula, in which we are going to depict the structure in order to give you a good idea how the bonding goes. Let me explain. Molecular formula for both of these compounds is C4H10. One of these, this one, is written like this: CH3, CH2, CH2, and CH3. If you count the number of atoms, you'll find out there are 4 carbon and 10 hydrogen atoms. While this one is arranged somewhat little differently, this one is CH3, CH, CH3, and there is another CH3 at the bottom.
Can you explain this word again? Can you repeat?
Yes,
CH3, CH.
Now, this arrangement is different from the one on the top. But look at the number of atoms. Both of them consists of 4 carbon atoms and 10 hydrogen atoms. So both of them has the same molecular formula, but both of them have a different structure. Later on, I'll come to tell you how we can write this or write this from these diagrams, but I haven't explained it yet because now is not the time. We are just discussing that molecular formula isn't useful enough in organic chemistry. That's why we come up with these formula. This is known as a structural formula. All right, because this explains the structure that all 4 carbons are present in a single row, or this explains the structure that 3 of the carbons are present in a straight row, while 1 carbon is either at the bottom or at the top of the structure. We call it a chain. Okay. So moving on, general formulae. This is the third type. There are many different families of organic compounds. We call them homologous series. Examples of homologous series are alkanes, alkenes, alcohols, carboxylic acids, esters. These are the ones that our chapters in organic chemistry are based upon. Every chapter is a separate homologous series in organic chemistry. Let's define homologous series for a better idea. A homologous series is a series of compounds with similar chemical properties because they have the same functional group. Each member differs from the next one by a CH2. Let's take a look. This is the simplest of alkane. The formula is CH4. Next alkane on the list is C2H6. The difference between both of these is 1 carbon atom and 2 hydrogen atoms, just like stated over here. The next one on the list is C3H8. And again, the difference is CH2. Next one on the list has the same difference, CH2. Alkenes are slightly different. The first formula starts with C2H4. The difference, however, is again CH2, whether you talk about the first step or the second. Alcohols are again different. This is CH4O or C2H6O or C3H8O. Again, the difference is CH2, no matter which step we are talking about. So for most of the homologous series, every step differs. But each of these homologous series, these compounds have similar chemical properties. Starting from CH4 to C4H10, all alkenes have similar chemical properties. All alkenes have similar chemical properties in themselves, and alcohols have their own specific set of chemical properties. That's why we call them a homologous series. Homo means same, logos means study. A series that can be completely studied. Why? Because the compounds behave the same in an entire series. All right, let's come to a point where we can describe them with a general formula. What I'm about to do is going to be extremely useful for you to understand how we are coming up with the formulae of these compounds, these entire series. For alkanes, the general formula is CnH2n plus 2. Whatever the number of carbon atoms, we multiply it by 2, we add 2 to it, we get the number of hydrogen atoms. Take a look. We have 1 carbon atom, but 4 hydrogen atoms. So if n is equal to 1, C is 1, H is 2 into 1, and then plus 2 to it, this is CH4. If C is equal to 2, H is 2 into 2, plus 2, so that is actually C2H6. If C is equal to 3, H is 2 into 3, plus 2, which is actually C3H8. Get the point? So general formula is a formula which can represent an entire series. No matter which step of the series I talk about, this general formula can always help you come up with the exact formula of the compound. For example, tell me how many number of hydrogen atom would be there. So I was asking you about alkanes, and I was telling you that the general formula is CnH2n plus 2. So I was asking you, what will be the number of hydrogen atoms present in a compound with 14 carbon atoms?
30.
Right. So talking about alkenes, the formula is simply CnH2n. As you can see that the number of carbon atoms is half than the number of hydrogen atoms. So how many hydrogen atoms would be there if the carbon portion is composed of 9 atoms?
18 hydrogen.
Okay. Predict the next member of this series in alcohols. This is CnH2n plus 2O.
Okay, so it's the same as alkenes.
Right, but just in addition of an oxygen atom.
Yeah, so there would be 10 hydrogen in the next one. And yeah, 6.
Predict the whole formula.
C6H
C5.
yes, yeah, wait. Okay, C5 and then H12O.
C5H12O. So that's pretty understandable. So the next one would be C5H12O. My bad. Okay. So this gives us a pretty good idea that the general formula helps us to come up with the molecular formula of a specific member of a specific homologous series. Only if we know the general formula for the series, we can always come up with the molecular formula of the next member or any member in that case. Okay, so continuing, the next on the list is the definition of functional group. Now, function group is actually a bigger, broader term. So we are just going to describe it as in a simplified form for now. I'm going to rephrase the entire definition again once we're done with this chapter and the next one on the list. All right. So for now, a definition in terms of baby steps would be functional group is an atom or a group of atoms that if is connected to a compound, an organic compound, determine the chemical properties of it. For example, if I add OH to an organic compound, it becomes an alcohol. And alcohols have their very specific properties. Though alcohols are famous in the world for drinking purposes, but they have a lot more chemical specifications and chemical usages than just drinking. Next on the list is this one, carbon-carbon double bond. If carbon-carbon double bond is present in an entire structure, and if just one carbon-carbon double bond is present in an entire structure, it becomes an alkene. All right?
Yeah.
Okay. So an atom or group of atoms may determine the chemical properties, or that may impart specific chemical properties to an organic compound if they're attached with them. Moving next on the list, we have structural formulae. Structural formula actually tells us how many atoms in the molecules are joined together by what kind of bonds.
Can you go up a bit? I was copying the functional group definition. Thanks.
So you want me to do what? Repeat the definition?
No, I was just copying it, so I knew it.
Okay. Continue. When you're done, let me know.
Okay.
All right, next on the list is structural formulae. Structural formulae actually tells us about the structure. Of course, it's going to tell us how many atoms are there in a molecule and in what way are they joined together. This can be drawn in two forms. One of them is displayed formula, which actually depicts the whole full structure. And the other one is a condensed form in which we can omit carbon-carbon single bonds or carbon-hydrogen bonds, and we can write it in a very small way. Okay, let me explain by giving you an example from both the structural formula and the displayed formula. The example we have been discussing is C4H10, and this is the structure. This is the model actually. This is the displayed formula. It gives us all the atoms of carbon, all 4 of them, all 10 of the hydrogen atoms, and literally all the bonds. This tells us that there are 3 carbon-carbon single bonds, and there are actually 10 carbon-hydrogen single bonds. So a displayed formula tells you about the exact number of covalent bonds present in a molecule of a compound. However, all of this can be shortened up. Let me explain. This carbon is bonded to these 3 hydrogens, so we can shorten it up to CH3. Then it is bonded to the next carbon atom. This carbon atom actually has just 2 hydrogen attached to it, so we can simply write CH2. Then the next carbon atom, this one with the bond, this one also happens to have just 2 hydrogen atom attached to it, so CH2 again. And then comes the last carbon atom, which happens to have 3 hydrogen atoms attached to it, so CH3. Or you can simply remove these bonds as well. You can write CH3, CH2, CH2, CH3. So both of these forms are known as condensed forms. Condensed forms actually remove all carbon hydrogen. You would see that in the first form, we removed the carbon hydrogen bonds out of it. So this big structure actually condensed down to a smaller one. And in the second structure, we removed both the carbon-carbon and the carbon-hydrogen bond. So this big structure actually came down to even a smaller structure than the previous condensed structure. So that's how a displayed formula and condensed formulas can be described. Make sense?
Yeah.
Okay. It's important to remember when you draw structures that carbon always forms 4 bonds, hydrogen always form 1 bond, oxygen would form 2, any of the halogens such as chlorine, bromine, iodine would form 1, and let me explain, nitrogen is going to form 3 bonds on top of this list. So it's pretty easy. If I write them all, instead of just writing 1, I would write it like this, that carbon is capable of forming 4 bonds. I usually add silicon to the list as well. In fact, let me add silicon right away to the list. Carbon and silicon are capable of making 4 bonds each. Hydrogen, fluorine, chlorine, bromine, I mean all the halogens are capable of forming 1 bond each. Oxygen and sulfur are capable of forming 2 bonds each. Nitrogen and phosphorus would be capable of forming 3 bonds each most of the time. All right. So this can explain the entire organic chemistry and covalent bonds throughout the book. Okay. So especially in organic chemistry, as we will mostly be dealing with carbon, hydrogen, and oxygen. So carbon forms 4, hydrogen forms 1, oxygen forms 2 bonds. Keeping that in mind would make sure that every time you can check your structure. Let me check this structure in front of you. Take a look at this structure, the same one we have been discussing. This carbon is making 1, 2, 3, and 4 bonds. So this carbon is drawn correctly. The next carbon on the list is also forming 1, 2, 3, and 4 bonds. If you look at all of these carbon bonds or all of the hydrogen, you would find every hydrogen forming 1 and every carbon forming 4 bonds, and thus they're stable according to the octet rule we have studied in the covalent bonding chapter, or the duplet rule for hydrogen. Make sense?
Yeah.
All right, good. So moving up next, there is one type of formula that is not described over here. However, we described it back in covalent bonding chapter, and that was dot and cross formula. Do you remember that?
Not really. It's been
in
a long
which
time
we
since.
used dots and crosses to represent the outermost electrons in shells of different elements. For example, we used to describe methane like this. Like this. Now, in the overlaps of the circles, you would find the electrons that have been shared. So the methane has structure like this. Carbon is making 4 single covalent bonds with 4 different hydrogen atoms at the same time. Hence the formula of methane, CH4. This is the structural formula, and this one is the dot and cross formula. We studied dot and cross formula for covalent compounds as well as for ionic compounds back in Unit 1, covalent bonding and ionic bonding chapters. So this is another kind of formula which can be explained over here, but the book never included it in this chapter though. Are we good?
Yeah.
Okay, so revising, keep that in mind that the first one on the list was empirical, the second molecular, the third general, the fourth one structural, the fifth one condensed or displayed formula. The sixth one on the list is dot and cross formula. So we have many different types. Make sure that you understand what the examiner asks for. He can ask you to draw any kind of formula. Okay, now how to draw structural formula? For anything other than the smallest molecules, drawing a fully displayed formula is a very time-consuming structure. So what we do is that we condense them up into condensed structures. We try not to show carbon-hydrogen bond as I just explained. So I give you the same explanation for butane, writing in this way or this way. I hope you understood those. So
Yeah.
Let me tell you that even if they don't look the same, they're actually the same molecule. This is a kind of confusion that confuses students in exam. But if you take a look at this, all have the same formula. All of them have 4 number of carbon atoms, 10 hydrogen atoms, and they're all linked to one another in a straight chain, whether be the chain like this, or the chain goes like this, or the chain goes like this, they're still straight. Okay?
Okay.
So don't get confused by a simple twist. However, if something is present on top or at the bottom of the chain, in its center, not at the corners, not like this one is at the corner. These bends are at corners. If the bends are present in the center, then it definitely has a different chain, a different formula probably. I mean, a different structure. Okay. So when you're asked to draw a structure for a molecule in IGCSE, always draw it as displayed formula. You can't lose any marks by doing this. Whereas you might lose marks when you're drawing simplified form. Only draw these simplified or condensed structures if you have a good grasp on them. Otherwise, try preferring the complete displayed formula, because that way you would be able to check and make sure that you're not making mistakes. Okay?
Yeah.
Most of the time, molecular models like these ones, are not asked as a question in exams. So drawing models won't be a good idea. Drawing structures, be them displayed structures or condensed structures, would be a very good practice. Okay. Now, this actually gives you a pretty good idea that this compound may twist like this. This compound may twist like this. This compound may twist like this. So actually, they are trying to explain you how these 3 structures and these 3 models look exactly the same. All right. So these are just twists in the structure, which we can show in the displayed formulas as well. This does not mean this is a different compound. These are all different forms of the same compound. Okay. In fact, just a little bit of twist, not even completely different forms. However, if we are talking about a molecule that consists of a carbon-carbon double bond, drawing 2 lines between 2 carbon atoms as 2 pairs of lines or 2 pairs of shared electrons changes everything. It's not alkane, it's alkene, as we have discussed earlier, and this is showed like this. So we cannot write it like CH3, CH, CH2. Drawing a double bond sign in between is a better way to write it. Okay, this is not a good way. This is the correct way to write it. Get the point?
Yeah.
What we are trying to say over here is that you may skip all the single bonds you want to, but skipping a double bond or a triple bond, even in the condensed structure, is not a good idea. I hope you get the point now.
Yeah.
Good, good. So in IGCSE, mostly carbon-carbon double bonds will also be shown in the questions. Okay?
Yeah.
All right. Now, let's go for a small practice. What I'm going to do is that I'm going to close the book and I'm going to start a whiteboard screen. And I want you to go ahead and convert these displayed formulas into condensed ones or condensed formula into displayed ones.
Okay.
As a practice. This is your first one. As you can see, this is a condensed formula. So you are supposed to convert it into a completely displayed formula showing all the atoms and all the bonds.
Should I start?
Yeah, go ahead. Just to use a different color. And I'm going to write the next one on the right-hand side of the same page. Good. You're supposed to write both kind of condensed forms, the ones with carbon-carbon single bonds and the ones without.
Wait, so this is not correct?
Yeah, this is correct, but
No,
I want you to
this one right now.
Go ahead, whichever one you prefer.
Yeah. I'm just finishing this one.
So you're starting off with a condensed formula that contains carbon-carbon single bonds, or that shows carbon-carbon single bonds as a part of it. As soon as you're done with this one, move on to the other type, which does not contain carbon-carbon single bonds. So I want you to draw both of them.
Wait, so what do you mean by not? Oh, okay, wait, I get it now. Okay. So do you mean
not
like
this
one
one
with the bonds?
Just about the second question, not about the first question.
Oh. So what should I do in the second one? Without the bonds?
Without the single bonds, without the carbon-carbon single bonds.
So I just write the formula.
Right.
Oh. So like this.
Yeah, you are correct with your structures, except that you are correct with question number 1, but there is a small mistake in both the structures of answers to question number 2.
Oh.
Check it again. Question number 2 only.
Oh yeah, there's no.
Right. Good.
Yeah.
Okay. I want you to do a couple of things more for me. Why don't you go ahead and tell me the molecular formulae, both for compound 1 and compound 2?
Yeah. Okay.
All right. There are 2 kinds of hydrocarbons that we're going to discuss over here for now. The first one, alkanes, for which the general formula is CnH2n plus 2. The second category is alkenes, for which the general formula is CnH2n. Which category does these compounds belong to?
Alkanes, because they don't have the double bond.
Right. Also, because number of carbon atoms and hydrogen atoms conform from their molecular formulae according to the general formula to alkanes.
Yeah.
Right? Not just because of the double bond, also because CnH2n plus 2 conforms both C3H8 and C5H12 in it.
Yeah.
Get the point? Okay, good. This means we need to get back to the book. So, all right. So now you understand how to draw the structures from the formulae, or from the structures, how to write the formula. You now even know how to write the molecular formula. And of course, I never asked the question, but if I asked you to come up with the empirical formula, I'm pretty sure you would be able to do so. Okay, so continuing, naming organic compounds. This naming is going to be a little bit difficult, but what we are going to do is that we're going to study naming for different types of compounds a little bit separately. So I'm going to discuss a generic naming category or methods over here. Then what we are going to do with every upcoming chapter, I will revise that naming. For example, I'll first go with the naming of alkanes in the next chapter, alkenes in the chapter after that, alcohols, carboxylic acids. I'll keep on going with every chapter and then naming separately, as well as we're going to do the generic steps in here. So first thing you need to do is to code the chain length. Count number of carbon atoms in the length. And as you can see, for different numbers in the carbon atom, we have different code letters that we need to come up with. And these code letters are actually prefixes. Remember, prefix is the part of the name that comes first in the name. Remember, the first part of the name is known as prefix. The last part of the name is known as suffix. These are prefixes. We'll come up with the suffixes later. If the structure has 1 carbon in it, the name starts with meth, 2 eth, 3 prop, 4 bute. This is not but, this is bute. 5 pent, 6 hex. Although the book stops over here, but I would like you to know that we write hept for 7, oct for 8, non for 9, and dec for 10. Please make sure you note it down too, because this is going to help you with your papers.
Yeah. I've noted it down.
And of course, these kind of phonetics can always help you remember the exact order of these. Myth, eth, prop, bute, monkeys in, eat, pink, bananas, or whatever name you can come up with. All right. For example, butane actually has a chain of 4 carbon atoms. As soon as you read the name, you would come to know propane has a chain of 3 carbon atoms. Hexane would be a chain of 6 carbon atoms. Pentane would be a chain of 5 carbon atoms. As soon as you find out the prefix in any name, you would instantly come to know how many carbon atoms are present in that chain. Easy enough?
Yeah.
Okay, so let's move on towards suffixes because we definitely need to go with suffixes as well as the prefixes. Okay, coding for the type of compound. Alkanes are homologous series, similar hydrocarbons. They only contain carbon and hydrogen. All the carbon atoms are joined to each other with single covalent bonds. Compounds like these are coded with the ending "ane." Suffix means ending name. For example, ethane, eth means 2 carbon atom, ane means they're singly bonded. So that's how the structure is going to be. How do we come up with the structure? Let me explain you a few very simple steps to come up with the structure from the name. As soon as you read the name eth, you instantly came to know that there are 2 carbon atoms involved. The second part of the name was ane. Ane represents alkane, and alkanes are singly bonded, so you instantly come to know that they are singly bonded. Now you know every carbon makes 4 bonds, so go ahead with drawing 4 bonds on top of it. The rest of it is what? Hydrogen. Pretty simple. So hydrogen all the way around these. And there you go, you have the structure CH3, CH3. Now you know ethane is made up of C2H6. Now you know how.
Yeah.
Get the point?
Yeah.
So let me try again by explaining the major steps I just followed. My first step, and I'm going to redo it. Okay, this is going to help me a lot with it. So my first step was to draw the carbon skeleton by finding out the number of carbon atoms, eth. As soon as I studied the word ane, it meant there was a single bond in between. This is known as a carbon skeleton. It's better to start the structure from the carbon skeleton and not from the number of hydrogens. This is known as the backbone of organic chemistry. That's why I'm using the word skeleton. As soon as you're done with it, make sure every carbon is forming 4 bonds each. Second important step. The last important step, put up the hydrogens on all the sides wherever we had the bonds, and there you go. You have the entire displayed formula. Get my point?
Yeah.
So I followed 3 major steps. The first one, to draw the carbon skeleton. The second one, to make sure that every carbon is forming 4 bonds. And the third one, to fill it up with hydrogen in order to satisfy the valency or the number of bonds carbon is supposed to make. There you go. You're done with the entire displayed formula. The alkanes are as simple as that. Shall we move on to alkenes?
Yeah.
Good. Okay, coming on to alkenes, as you already know now, that they contain a carbon-carbon double bond. The name end in ene, E-N-E. So there is a huge difference between A-N-E and E-N-E. And by this huge difference, the students come down to such a point that making a small letter mistake in the name, and it changes everything in the structure. So make a mistake, and the mistake will change the complete identity of the compound. That's why mistakes like these are never allowed in exams, because this is going to give the examiner an entirely different perception about the compound. I hope you get the point, right?
Yeah.
Okay, so coming up next, ene is the one that shows it has carbon-carbon double bond. For example, if I come up with ethene, as soon as you read eth, it has 2 carbon atoms. As soon as you read ene, they have a double bond in between. Now, as every carbon is making a double bond, so there are only 2 hydrogen atoms that are possible to be linked with every carbon atom. There you go, it's C2H4, and that's the molecular formula or the structure for ethane. All right?
Yeah.
Now, as soon as we start drawing longer chains, everything changes. The position of double bond could vary in the chain. This is shown by numbering the chain and noting down the carbon atom the double bond starts from. Take a look. With 4 carbon atoms, the double bond may be present at the very corner of the chain or may be present exactly in the center of the chain. So as the double bond starts from the first carbon atom, 1, 2, 3, 4, this is but1ene. That's how it's named. First of all, the prefix of number of carbon atoms, a hyphen is a must, a dash, then the number carbon atoms or double bond starts with, not the one, because the double bond is connected both to the first carbon atom and to the second one, but you're supposed to write the smaller number in here. Then another hyphen, and then the suffix "ene." So every part of this name actually represents something. But represents that the structure has 4 carbon atoms. 1 represents wherever the double bond starts with, and ene represents that there is a double bond in the structure. However, if we change the name simply to but2ene, this gives you a pretty good idea. The number of carbon atoms and the double bond remains the same. However, 2 represents where the double bond is located. And of course, 1, 2, 3, 4. Does not matter if you start numbering from this side, 1, 2, 3, 4. Get the point?
Yeah.
The same numbering is shown over here for both the compounds, because in here they have shown the displayed formula. Take a look. You would know that in this case, what they are trying to tell you is that but1ene can be drawn from left to right or from right to left. It does not matter how you draw it. It would still be but1ene. None of these structures represent but2ene because both of these structures have the carbon-carbon double bond starting from the first carbon atom, no matter you start numbering from the left-hand side or from the right-hand side. And by this, you easily get an idea that if the double bond starts from the left-hand side, like this one, you start the numbering from left-hand side. And if the double bond starts from right-hand side, you're supposed to start numbering from the right-hand side. So much so that the carbon starting the double bond should get the lowest possible number every single time. So in this case, if the structure is already drawn, the numbering should start from left side. In this case, if the structure is already drawn, you're supposed to number it from the right-hand side. Why? Because that way, the double bond would get the lowest number for its carbon atom. Make sense?
Okay, so we just like, whenever we see the formula with a double bond, we just need to make it so it has the lowest number.
So right, the double bond should get the smallest possible number in the numbering. If you have to start from a numbering from the right or from the left or from top or from bottom, it does not matter. What matters is that the double bond, the starting carbon of the double bond should get the lowest possible number, smallest possible number.
Okay.
Okay. So I skipped a couple of hints on left-hand side, so I'm going to go through all of these. The first hint, in more complicated molecules, the presence of code AN in the name shows that carbon atoms are joined by a single bond. However, you can tell that propan-1-ol contains 3 carbon atoms by the name prop. N means that the carbon are singly bonded. And code at the end gives you more information about the molecule, which you're going to study in the later chapters. Not just that, both parts of this figure, figure 22.11, shows the same molecule. But in one case, it has been turned over so that what was originally on the left is now on the right and vice versa. It would be silly to change the name every time because the molecule moves, because molecules can easily move in solution or in liquid forms, even in gaseous forms. So both the forms have the same name, but1ene. Get the point?
Yeah.
Not to forget that this kind of structure, even they have different structures, even if they have different names, they are still isomers.
Remember the definition, same molecular formula, but different structure. This one has the molecular formula C4H8. You may count the number of atoms on your own. This one also has the formula C4H8. So these are isomers. Why? Because they have the same molecular formula, but they have different structure, different names as well. So yeah, if anything has a different structure, but the same molecular formula, we call them isomers. But isomers not just have different structure, they also tend to have a different name. Make sense?
Yeah.
Okay, good. So moving on, coding for branch chain. Here, when it becomes slightly an upstep, slightly little bit difficult than the previous ones. Previous ones were very easy. Now, hydrocarbons can have chains, side branches, branches on top or at bottom of the straight going chain. When that happens, what usually happens is that we only go with a couple of chains at this level, IGCSE level. The first one is CH3. This bond sign shows that this is a chain and can be put on top or at bottom of any structure, like this one over here does. This is methyl. Meth represents one carbon atom. Yl is the suffix for a side chain. Remember, all side chains have the suffix yl connected to them. This is ethyl. Eth represents two carbon atoms. And again, yl represents a side chain. Get the point?
Yeah.
But when you're going to name a molecule like this, let's try naming this molecule. The first step is to locate the straight longest carbon chain you can in the structure. Then the position of the side chain is shown by numbering the carbon atoms from wherever end of the longest chain produces smallest numbers in name. Remember, the smaller the number in the chain or the name, the better is your name and the correct your name is. If you come up with bigger numbers for the name, that's not a good idea. Probably the name would be rejected. You won't get marks for it. Okay, so let's try going through this structure. Now, you can predict this is the straight longest chain. Okay, you may also predict that this is the straight longest chain, right?
Yeah.
So you can either number this chain like 1, 2, 3, 4, or you may number it 1, 2, 3, 4. If you number it from top, this is the carbon atom where the branch is located. If you number from bottom, this is the number of carbon atom at which the branch is located. This is the branch. So number 2 is a smaller number than number 3. So this kind of numbering is wrong. And this kind of numbering is correct. If I go by the red system, let's erase the black system, and I'm going to go with the red system in order to make sure that you understand what I'm about to say. Now,
So the
if I go by
system
the
is correct one.
The red and the black are both correct. It's up to you that which system you'd like to perceive. Students perceive it differently. The way we name it can actually be conceived by many different methods. Take a look. I can come up with the numbering 1, 2, 3, 4, or I can come up with the numbering 1, 2, 3, or 4. This kind of numbering is incorrect because 3 is the number that connects the chain. Sorry, my bad. This is not the chain. This one is the chain, as it's connected to this carbon atom again. So this is the correct kind of numbering, right? So this is first carbon atom, this one at the bottom. This one is the second one, this one third, this one fourth. Get the point? So it does not matter how you perceive the longest chain. If you do the numbering correctly, you will always end up with the same name.
So if we just took the black part, if we just took the longest chain, it would still be 4. So that's correct as well.
Yeah, that's correct as well.
Okay.
If you're considering the longest chain in the correct way, you will always end up with the same name. For example, How to write this name? First of all, write the number to which the chain is connected. Then put a hyphen because any number and any letter in organic naming is always separated with a hyphen or a dash. Hyphens are very important. Remember, numbers and letters in organic names are always separated with a hyphen. Like on the previous page, we were writing but-1-ene. Why? Because a hyphen should be placed the next part of the name to it. Either the name is put previously than the number or after the number. There should be a hyphen to separate the numbers and letters. Get the point?
Wait, but why is this 2-methylbutane?
This is two
It's not an
hyphen.
alkene, so there's no double bond. So why is there 2?
This 2 represents the number at which the branch is connected. This 2 does not represent the double bond alone. So the numbering does not have to specifically denote the double bond. Numbering also represents a branch. Make sense? So the numbering may represent a double bond, but how would you know there is a double bond? By the suffix for a double bond. But if along with the numbering, the suffix is "-ile", it represents a branch. So it's not number which is the representation for the double bond. It's actually the suffix. Number is just to locate it.
But what if
It's
we
the
use the
suffix.
back method? If we use the back method, won't it be 1, 2, 3? So 3-methylbutane.
I don't get it. Say it again.
So you know the back method was like it was 1, 2, 3, 4, like in a straight line. So the first one would be 1, the second would be 2, and then the third one would be 3, which has the branch thing.
But that
So
was
won't it
the
be 3?
wrong technique. I told you that was the wrong technique. Okay, let me do it on a whiteboard because the book is a little bit messy. Okay.
Yeah.
I'm going to draw the same structure on the whiteboard. Let's take a new one and let me do it in a different color. Okay. So this is the structure we are currently talking about. This is 2, this is CH3, and this is CH3. According to my black numbering, this one was supposed to be 1, 2, 3, and 4. This is the correct numbering. I intentionally did this numbering 2. This is the branch we're talking about. And this I said is the incorrect numbering because 3 is a bigger number. 2 is a smaller number, so this is the numbering we're going to prefer. So the name would be 2-meth because there is a single carbon in the carbon branch, "-ile", which represents the branch, "-but", which represents the parent chain. This is known as the parent chain. And this is known as the branch. So "-but", because there are 4 carbon atoms in the parent chain, and "-ane", because they are all singly bonded. And what I did was that I came up with the grid numbering in the structure. Let me do that again for you so that you would understand how the name is same, whether we go with a grid numbering or we go with a blue numbering. This is the kind of numbering I came up with. In case of red, this is number 1, number 2, number 3, number 4, or 1, 2, 3, and 4. And I said this numbering is incorrect. This numbering is actually correct because 2 is a smaller number. Again, 2, the number of carbon atom at which the branch is located. This is the branch. Dash, meth, because branch has, this is the branch, and then this is the parent chain. These are the specific words that we only use in organic chemistry. So there is only 1 carbon atom in branch, hence meth. "-ile" is the suffix for branch. "-but" is for the number of carbon atoms present in the parent chain. "-ane" represents that the parent chain is singly bonded. There you go.
Yeah.
In both the cases, whether you come up with the straight longest chain in the red method or out of the black method, you will end up with the same name if you do follow all the steps of naming correctly. That's the best part about naming organic compounds, that it is designed in such a way that if you perceive slightly differently in terms of locating the longest straight carbon chain, you will still end up with the same name as your friend who also has followed the same set of rules as you, who just happens to perceive the straight longest chain in a slightly different way. But both of you would be correct and both of you would end up with the same name. That's the beauty of it.
Yeah.
Make sense?
Yeah.
So let's get back to the book then. We are going to practice with you with different compounds, but after I explain a couple of things more. So what I was explaining was that there are two types of side chains that usually are a part of IGCSE. Okay, and how are we supposed to come up with a name? There are other ways of describing this too. Now, this is the case where the straight longest chain has two branches on the same carbon atom, one on top and one at bottom. How are you supposed to do it then? Now, some new rules. If you have two branches, not just one, you're supposed to represent them with two numbers. Remember, the numbers are separated by commas, whereas numbers and letters are separated by hyphens. Make sense? These are the rules of organic chemistry naming. Now, as there are two methyl groups, this one is also a methyl, this one is also a methyl. Both happen to be branches, both happen to contain one carbon atom only. So we'll use a prefix di. Di means two. Tri means three. Tetra means four. So there can be either two branches, maybe three branches, maybe four branches, maybe even more. All right. So two represent that both the branches are on the same carbon atom, as they both of them happen to be at the second carbon atom, right? Dimethyl, because both the branches have one carbon atom. Prop means the parent chain has three carbon atoms, and ane means the parent chain is singly bonded. So every part of this name represents something. Let me explain again. The 2 and 2 means that both the branches are present on second carbon atom. Di means that there are two branches. Meth means both the branches have single carbon atom. Ile represents the suffix of the branch. Prop represents that there are three carbon atoms in the parent chain. Ane represents that those carbon atoms in the parent chain are singly bonded. So every part of the name has its purpose. Clear enough?
Yeah.
Now, you should be capable of reversing this process, trying a structure from a name or from the name, the structure. I mean the name from structure or structure from name. Right?
Yeah.
Remember, when you are converting a name into the structure, always go with the carbon skeleton first and the rest of the structure after. So let's practice. So I'm going to go back to the whiteboard. Let's open up a new one. And let's see. I'm going to use this one as a color. You should be using a different one.
Yeah.
As a start, yeah, an easier name to begin with.
Okay.
And I'll keep on giving you structures. You may keep on writing the names. So the second one on the list would be.
Wait, should I annotate or should I just say the name?
Yeah, just go ahead and write the name.
Okay. Is this one correct?
Yes, it is, but the name is not supposed to have spaces in between. 2-methylpropane is a single name. No hyphens, no spaces.
Okay.
Okay. Yeah, I
Yeah.
understand you're trying to write the straight name, but from the next ones, try removing these spaces too.
Okay.
Okay. And yeah, you're correct with this name. And I've tried to play a small trick on you in compound 2. Let's see if you can follow the trick or not.
Yeah. So would this one be 1 or would it be 4? Would the next number be 1 or 4?
Think again. That's the trick I was talking about. First of all, try locating the straight carbon chain by drawing a box around it. Like I was doing everything on purpose, drawing a box, drawing the circles, numbering them. Is this the longest chain?
Wait, so it would be this one.
Okay, let me tell you, this is not the straight longest chain. Yeah, this one is the straight longest chain. So it turns out it only has one branch. This now seems easy to number. Go ahead, number it. Tell me the name.
Okay, so 1.
In organic chemistry, we call it a trick of twists. I mean, if you twist the structure, actually, there is mostly no changes in the name of the structure. So it's known as a trick of twists. Don't get tricked by twists.
Okay.
Okay. Okay, once again.
Yeah, no spaces.
No, it's not about space. Let me tell you, the number in the name is not correct. Try coming up with the lowest possible number. Start numbering from the either side wherever the branch gets the lowest possible number.
Yeah. Maybe 2.
Good. Now you're right.
And 2.
Good. I guess now it's making sense to you more and more. The more you practice, the more it makes sense. Okay, let's continue practicing because we still are supposed to practice the compounds that consist of 2 branches instead of 1. So the third one on the list is this. Okay, the fourth one on the list is this. You can keep on writing the names and I would keep drawing the structure. Okay.
Is this one correct?
Good, that's correct. What about the fourth one? Okay, remember, if there is a prefix like di written in the name, then there must be two numbers in the name. And this name is only showing me a single number.
Wait, so would it be 2 and then comma 2?
Yeah, there should be two twos. So 2 comma 2
Yeah.
hyphen and then dimethylbutane. Now it's correct.
Yeah.
Now,
Is this one correct?
yeah, this one is correct. Now, let me try and play another trick on you. This time it's not going to be a trick of twist. This time it's going to be a different one. Now, you have dealt with enough branches of methyl. Let's try and go with a branch of ethyl, all right?
Yeah.
My bad. Small mistake. Try naming this one while I write the next one. Good. So far, so good. No, actually, this whole comes as one branch, and this one is ethyl.
Oh.
So this whole
Okay.
thing becomes one big circle.
Oh yeah, so this becomes, yeah, okay.
Instead
Ethane
of
ethyl,
yeah. Right? Instead of methyl,
yeah.
this branch is known as ethyl.
Yeah.
So the name becomes?
So 1, 2, 3. So would it be 3 and then ethyl?
Ethyl, right?
And then hexane.
Right. Hex because it has 6 carbon atoms, and ane because they're all singly bonded.
Yeah.
And 6 has the trick that I was talking about. 5 is pretty simple. 6 has a new trick. Not the trick of twists, but another one. Well done. You didn't fall for the trick.
Yeah, thank you.
Sometimes students tend to think that this is an ethyl branch instead of just going with the longest chain and proving that it does not contain an ethyl branch. Instead, it contains a methyl branch. Very good.
Yeah,
So now,
I was going to write that first.
yeah.
Okay, good. Now, there is one simple rule that I still need to explain that has been a part of past papers. I'm not going to explain it with the help of the book. I'm going to explain it with the structure I'm just about to draw. Okay, so there you go. So about this chain. In fact, before I explain what I was about to explain, why don't you go ahead and just in this locate the straight longest carbon chain and try numbering it.
Okay.
And when it comes to naming the compound, then I'm going to help you with it.
So there can be multiple chains.
Yeah, but only one of them is the correct one.
Oh.
Actually, any of them can be the correct one if you're following all the rules. And if you follow all the rules, there are 3 possible straight longest chains.
I went for this one because I think it would be easier when I'm naming the compound, because over here, if I made one like this, then I have 2 of these compounds.
Actually, tell me, how would you name this entire branch? You don't know how to name it. So you need to go with a different set of a long chain. Try going with a different long chain because this won't help you. You don't know how to name this chain. Yeah, other than this one.
Yes, this straight one.
Yeah.
Because then I know how to name this one, but I'm still not sure about this one.
Yeah, one of them is methyl and one of them is ethyl. That's what I was talking about. Let's start numbering from this side because that way both the chains would get smallest possible numbers, right? If I start numbering from this side, this would be numbered as 3rd, this would be numbered as 4th. Instead, 2nd and 3rd are better numbers. What I want to explain in this case is that you would notice that at 2nd, we have a methyl chain, and at 3rd position, we have an ethyl chain. Now, we may write ethyl first or we may write methyl first. Let me tell you, they're written in alphabetical order. As E comes before M in alphabetics, that's why 3-ethyl would come first, 2-methyl would come after, and pentane. Make sense?
But for the ethyl chain, there's 2 carbons, but there's 5 hydrogens. Shouldn't there be 6 hydrogens?
If there are 6 hydrogens, the carbon won't be making 4 bonds each. As soon as you put 3 hydrogen over here, this carbon is making 4 bonds, which is actually not correct. The carbon is supposed to make a maximum of 4 bonds.
Okay, so when we're answering these types of questions, we just look at the carbons. We don't look at the hydrogen.
Right. You just look at the carbons. When you're naming them, when you're drawing them, you also look at the hydrogen atoms. So you would make sure that every carbon is making 4 bonds. No, not a bond less, not a bond more.
Yeah.
All right.
Can you explain this part again? Why 3 ethyls before 2 methyl pentane?
Because in alphabetical order, E comes first and M comes after. The branches are supposed to be put in alphabetical order. All right. So ethyl comes first and methyl comes after. That's why. And the starting names, the letters of branches matter, not the entire parent chain or anything else. All right.
Yeah.
Okay, so let's get back to the book then. Okay, so these are the structures for butene.
And they are trying to tell you that whether you put the CH3s up or down does not matter. Okay?
Yeah.
All right, moving on. Structural isomers. Now, as I have been saying earlier, we are going to go for isomerism, the phenomenon in which they have the same molecular formula but different structure. So isomers of C5H12. Take a look. This is C5H12, a straight chain compound. C5H12 with one branch, C5H12 with two branches. All of them have 5 carbon atoms and 12 hydrogen atoms each. This one is named as pentane, this one is 2-methylbutane, and this one is 2,2-dimethylpropane. They all are isomers of C5H12. They're known as isomers because they have the same molecular formula, but different structural formula or different displayed formula, or simply speaking, different structure. Now, what happens is that we give them different names because they have different chemical and physical properties. This one would have a different melting or boiling point or density than 2-methylbutane or than 2,2-dimethylpropane. So that's why studying isomerism is very important. Okay, the common question in past papers are to draw 2 or 3 isomers of the same compound. As soon as they tell you that the formula, molecular formula of the compound is this, we tend to ask our students that you can draw different isomers on a simple principle. Draw the first isomer as a straight chain, like pentane. Try drawing the second isomer with just one branch, and try drawing the third one with 2 branches. It's pretty easy. Always draw the carbon skeleton based on the number of carbon atoms first, and then you can go ahead and give it hydrogen atoms to show the entire displayed formula. In this case, it's pretty easy. Draw 4 carbon atoms, and remember, the branch is supposed to be on central carbon atoms, not at the corner ones. There you go.
Yeah.
And now, in order to draw hydrogen, you can simply draw these on top, at the bottom, or at sides to make sure that counts well. You can do the same over here, like this. And there you go. And in this case, the skeleton could be drawn like this. Only the central carbon can have more carbon atoms. There you go, 2 branches. Then go ahead and give them hydrogen atoms in order to make sure that they have 4 bonds each and they satisfy their valencies. There you go. So you can draw these structures right out of this molecular formula. And you can draw different isomers. So it's pretty easy. If you get a straight chain compound, try drawing branch chain compounds, the compounds with branches, either on top or at bottom with 1 branch or 2 branch. It entirely depends upon you, but that's the way to draw isomers. And if they give you a branch structure and you're supposed to draw an isomer, try going for the straight chain. This is a pretty good way of drawing isomers. All right?
Yeah.
Okay, let's practice. I want you to go ahead and draw 2 isomers for this compound.
Okay.
And afterwards, when you're done drawing the isomers, give them names too.
Okay.
What was the date that you were mentioning for your organic chemistry test?
16th March.
16. So we have time to practice. All right.
Yeah.
Continue.
I'm just gonna write this formula so it makes it easier to understand.
Sure. You can draw displayed formulas. You can write condensed formulas. Both are fine with me. If you just want to write condensed formulas, you can. It's completely all right. Remember, in exams, if they don't specify the type of formula that you're supposed to write, it's completely optional whether you write the displayed one or the condensed one. In either forms, you'll get complete marks if you're correct.
Okay.
Remember the carbon skeleton first and the hydrogens after.
Yeah. So we can do.
And remember, before 16th, we would need more classes than just a couple.
Yeah.
You might need 3 to 4 classes because organic chemistry seems like one page, but practice takes more time. And without practice, you won't be able to do it correctly on the test date.
Yeah.
We can't go through organic chemistry without written practice. I mean, if I don't do that and I do all of it orally, that won't help. You will make a lot of mistakes in your first test.
Yeah.
So try taking out some time for our classes before 16. Try planning them beforehand and let me know when you want to put the classes, right?
Okay. Yeah. So would
I'll
this
try
be
to
correct?
spare time for our classes. And yes, you're correct.
Yeah.
Let's come up with the names then.
Yeah.
Good.
So 2-methyl propane.
Very good. So now you would notice that you have 2 isomers in total for a compound that has 4 carbon atoms. Getting back to the book, this is the point I wanted to prove. Getting back to the book explains about C5H12, and you would notice that there are 3 isomers for C5H12. So the compound that has 6 carbon atoms would have 4 or 5 isomers. Moving on, the compound that has 30 carbon atoms has 4 million possible isomers. That's why organic chemistry is so big. If only one compound can have 4 million possible isomers, all of them having different chemical and physical property, that's why we have billions and trillions of compounds in organic chemistries and billions and trillions of limitless possibilities
of different physical and chemical properties based compounds. That's why organic chemistry, even a small part of organic chemistry, has more compounds than entire inorganic chemistry has. Inorganic chemistry is made up of 116 other elements, and the organic chemistry alone, which is made up of just carbon and hydrogen, 2 elements in total, has far more compounds than inorganic chemistry. I think now it makes much more sense why we have such a big difference in organic and inorganic chemistry, right?
Yeah.
Good. So moving on, they have told you the same thing, that how to come up with the carbon skeleton first so that you can draw the rest of the structure later. Remember, a straight chain structure is known as an unbranched chain. So this one is either known as straight chain or unbranched chain, both the names. And this one are both branched chains, right?
Yeah.
Now, the name for this one contained one branch. However, this one contained 2 branches. So the prefix di is easily going to indicate that there are 2 identical branches in this structure. Make sense?
Yeah.
Okay, moving on. So students frequently think they can find another isomer as well. If you look closely at this 4th isomer, you would notice that this isomer is just rotated in space as the second one. This one is still 2-methylbutane. All right?
Yeah.
So there are only 3 isomers for a compound that has 5 carbon atoms. If you can come up with other isomers, they would just be rotations of the similar isomers you have previously drawn. So don't push it more than what it actually has. You might come up with a wrong structure or a name or something that has been previously used. From this rotation, we get a pretty good idea. We can explain structural isomerism. Molecules that have the same molecular formula but different structural formula are known as structural isomers. The phenomenon is known as structural isomerism. Now, the atom in different isomers are joined in slightly different order. That's what's the basis of entire isomerism. There is another form of isomerism which is known as optical isomerism. Optical isomerisms have atoms joined in the same order. They even have the same structural formula, but are arranged differently in 3-dimensional space, just like the mirror images. Remember, the left hand and the right hand of a human being are exact mirror images to one another, but they cannot be superimposed. You cannot put one hand on top of the other and both of them would not look the same. If you try putting this hand on top of this one, you would notice that the thumb of the left hand comes on the right and thumb of the right hand comes on the left, right? If you try to put both hands on top of one another. Make sense?
Yeah.
For this specific action, we use the words cannot be superimposed, means they cannot be put on top of one another. Just like this structure, if you try to put this mirror image on top of this structure, the blue of the right one comes on the left and the left one comes on the right, or vice versa, right?
Yeah.
In this specific case, when the structure are mirror images of one another and the carbon atom consists of 4 different portions or parts on itself, that carbon is known as chiral carbon. The way it's pronounced is chiral, not chiral. Chiral is not correct, all right? But there are 2 conditions for chiral carbon. One, it must have structures that have mirror images of one another. Secondly, as these are 4 different colors, what they are trying to pose over here, that it consists of 4 different sets of structure. Means
if there is carbon and this one, this one, this one, and this one has to be different. Let's say this one is CH3, this one is chlorine, this one is oxygen and hydrogen, and this one is bromine, then this carbon can be taken as chiral. Why? Because all four sides have different set of atoms. It would be chiral once it has a mirror image like this one. See, it's a mirror image of one another. At the same time, it's connected to four different sets of atoms. So this carbon would become chiral carbon. So there are two conditions for chiral carbon. This is a look ahead. They are trying to explain you something right out of A-levels book. Most of the time, the screen portions are not taken for exams, as is this one. All right. So they are not going to go with this kind of question. Don't worry. They're just trying to prepare your minds for A-level course. They may ask about optical isomers. I mean, up ahead till the definition, it may be a part of the question paper, but examples will not be a part of question paper. Although I explained the examples too, just to be on the safe side, but you won't need it. All right. So the left-hand side and the right-hand side are actually rotated 180 degrees in space, but you cannot put one on top of the other. Optical isomers have identical chemical properties, except when they interact with something that is also chiral. When they interact with something also chiral, they tend to show different set of properties. For example, apart from glycine, all naturally occurring amino acids have optical isomers, which means all the proteins in our body are chiral. That is why we can distinguish the two optical isomers in our body separately. One spells, for example, there are two optical isomers. One smells of spearmint and other of caraway seed, because the two molecules interact differently with protein receptors in our noses. They're exactly same structures, but there are mirror images of one another, so they smell entirely different with the proteins in our body. What we do is that we usually tend to use the words R and S to show their configuration. R and S mostly work like the right hand and the left hand side. Well, we have different words for R and S in chemistry. We don't exactly use the word right hand or left hand side for mirror images. Well, as that's beyond the syllabus requirement, so I'm not going to waste any more time in this. But what this paragraph means is that the two different optical isomers may have two entirely different set of properties. Right?
Yeah.
For example, this is an drug molecule A and B. They're optical isomers of one another. A have found to have B found to have anti-nausea effects, and they started producing this drug. Unfortunately, along with B, some optical isomer A was produced. And they came to see that because of molecule A, many children born in that era were found to have deformed limbs. One was treating morning sickness or anti-nausea effects in pregnant women. The other one was causing to have their children deformed limbs. This is as much as the optical isomers can have their effect on our body. One can be a very useful drug, and the other one can be a big disaster. Right? That's why medicine has always to be prescribed by the doctor and properly manufactured. If you make a small mistake in manufacturing of the medicine, you may wind up having a big trouble for the mankind. This was optical isomer for alkanes. The next topic on the list is structural isomers in alkenes. Ethene does not have any isomers. There are only two carbon atoms. How many different ways we can arrange it? No way, actually we can't. Propene doesn't have a structural isomer. That is still an alkene. So structural isomers would actually start from butene.
Like you can have but1ene or but2ene or 2-methylpropene. All of them have the molecular formula of C4H8, but they have different structures. Actually, to be honest, in this case, both of them are straight chain structure. It's just the position of the double bond which is different in both the cases. However, this one even has a branch and different from both the ones on top. All right?
Your voice was dying. Can you repeat?
Okay, I was saying that the two structures on top are actually just the position of double bond that is different. Take a look. In this, the double bond is in between the first and second carbon atom, and the one on the right has the double bond in between second and third carbon atom on the right.
Yeah.
But the one at the bottom actually has a branch in its structure. So that one is actually different from both the ones on top. Hence, it's also named differently, which also gives you an idea that branch may exist even in doubly bonded structures. All right?
Yeah.
Okay, I unintentionally skipped this extension work. Let's go through that too. Structural isomers of C3H6 doesn't have a carbon-carbon double bond. It has carbon atoms joined in a ring. We call it cyclopropane. Most of the ring-based structure have the word cyclo in them. It's something like this. This one is also C3H6, but it's not doubly bonded.
Why is it H2C?
You can write it CH2 or you can write it H2C. That's fine.
Oh, okay.
Means I can write it like this too. It would still be the same structure.
Yeah.
With this structure, I'm just trying to explain that the bond is in between carbon and not in between hydrogen and carbon. That's why I, instead of writing like this, wrote like this.
Yeah.
Okay. The molecular formula is C3H6, similar to propene, but propene has a double bond and cyclopropane does not. All right. That's the point they were trying to prove. Okay. Moving on. Yep, next they are going to give, just a second, let me check what do we have next. A quick look at the alcohols. Up next are alcohols. Now, we are now going to get out of hydrocarbons. Hydrocarbons were the compounds that were completely composed of just two elements, carbon and hydrogen. As soon as we're going to move on to alcohols, it won't be a hydrocarbon. Why? Because there would be a third atom, oxygen, involved in all of the structures. Alcohols are the homologous series of organic compounds, which will all contain an OH functional group attached to the hydrocarbon chain. So what we do is that in the naming, we're going to give it as a suffix ol, O-L. As soon as you see this suffix, you would automatically understand that the structure is an alcohol. Make sense?
Yeah, so, okay.
All right. Do you want me to redo some parts?
No, it's fine.
Okay. So moving on. These are the smallest four alcohols which would probably be a part of exams. Higher alcohols are usually not a part of the exams. The first one is methanol. As the name suggests, meth means it only contains one carbon atom. AN means that carbon atom is singly bonded. And OL means there is a functional group OH present to it. Next one in the list is ethanol. Eth means there are two carbon atoms. AN means they're singly bonded. And OL means alcohol functional group OH is also connected to them. Then there is propan 1-ol, which is specifying the position of OH as per its carbon atom it is attached to. And then propan 2-ol, which is specifying the position of OH
attached to which carbon atom in the chain? Both propane 1-ol and 2-ol are isomers to one another, and it's the position of the functional group that changes the name and hence their properties. Make sense?
Yeah.
This also tells you how to name the alcohols. So you're going to include the number of carbon atoms prefix in the chain. And instead of writing the whole word A and E for singly bonded carbon atom, we just skip the E. Why? Because we have another suffix involved, which tells us that it's an alcohol. So this part of the suffix tells us that there is carbon-carbon single bonding, and this part of the suffix tells us that there is an OH group attached to it. Make sense?
Yeah.
All right. So that's what I was talking about. As soon as we start a new homologous series, every time we're going to start with the naming techniques first. Okay. So before I move any further, I want you to go ahead and draw the structure of butane 1-ol for me, as well as butane 2-ol. Go ahead.
Okay.
So far, so good.
So would this be correct for butane 1-ol?
Right. Let's draw butane 2-ol.
Wait, for 2-ol, what difference does the 2 make again?
It's present on the second carbon atom and not on the first one, because in this case.
Oh, yeah, I get it now. I remember.
Good. Go ahead then. Good.
So
Well
this
done.
week, yeah.
This would be butane 2-ol. Okay, let's get back to the book. All right. So now you know, and let me tell you another thing over here. If you face a question of isomers, which is about functional groups included in them, not just alkanes or alkenes, the functional groups like alcohol does, then what you can simply do, if the functional group is present on the corner carbon, first carbon I mean, you can simply move it to the center carbon so as the number in the name would change, and there you go, boom, you have a new isomer. Get the point? So moving the functional group from the corner carbon to the center carbon, and from the center carbon to a corner carbon is a pretty good way of coming up with a new isomer of the compound. Make sense?
Yeah.
Okay, good. It is also possible, I mean, with the extension work now, it is also possible to find a structural isomer of propanol that does not have an OH functional group in it. For example, this is an option in which oxygen atom is actually bonded between two carbon atoms rather than it would have a hydrogen atom, OH bonded to it. This compound is named as methoxyethane and actually belongs to an entirely different homologous series called ethers. So yeah, two different homologous series may have the same molecular formula, but different structure. Make sense?
Yeah.
Just like we did back in alkenes and cycloalkanes.
Yeah.
Okay. Next up is chemical reactions. I'm going to keep them for the next day because they would require a lot of practice. We won't be able to complete it right now. Though we still have like 5 to 7 minutes left of our working, but they would even take more than 5 to 7 minutes. The balancing of equations may seem simple, but actually there are some few formulas involved that I'd like to teach you at this point, just to make sure you can manage time and balance these equations as quickly as you can, saving yourself a lot of time that other students mostly don't. All right?
Yeah. Would 2 more classes be okay for the test to revise for?
I don't think so. Okay, let me explain myself. Just a second.